Okay, so let's get started. Um, let's do a quick recap of what we did in the last class. We started looking at um, what is called the convex combination, right? So we saw what a convex set is, and I also gave some intuition about why you need convex sets, and then we looked at how to make something which is not convex into convex, right? Towards that, we looked at convex combination. What do you mean by convex combination of some k points? And subsequently convex set that converts a non-convex set into a convex set. Then we also looked at what is called the conical. Well, I left that as an exercise. So one way of how do you get a conical? You just pass, a line from the origin through all the points, and then take the convex hull of it. So that will give you the conic hull, right? As an example, we looked at half spaces. Half spaces turned out to be a convex set. Then we looked at an example wherein, so of course, the intersection of convex set is a convex set. We saw the proof. And then we looked at a specific linear program where the constraint set corresponds to the intersection of half spaces. So it's a convex set. We also, I basically gave some intuition about how to solve a linear program. Not how to, but what to expect out of a solution of a linear program. Then we started looking at what is known as convex functions, right? So we characterized what a convex function is. So basically, you take any 2 points, draw a line between the two. All the values on that line will be above the function, right? So we mathematically characterized that. And then we looked at a few consequences of this. One consequence was f of x is greater than or equal to f of I plus x minus y transpose times the gradient of f of I, right? So this is true for any xy in the domain of the function for any convex function. Then we also looked at a few other consequences. For example, if you look at the remainder form of Taylor series and use the consequence of the convex function, it turns out that the Hessian is positive semi-definite, right? So the other way is also true. Maybe we will come back again a little later. So I gave some intuition of how to prove it. You write these two equations. So the inequalities are true. Inequality is true for any convex function. So you basically use that inequality to prove. So what do you do? So basically, you look at on the left hand side. So the intuition is this, right? So you have f of the linear combination that should be below the line, right? That's what you'll end up doing. Okay. Anyway, so let's get started today. So we looked at a few other functions, right? E power x is convex, minus log of 1 plus x is convex. So that means log of 1 plus x is concave, and so on. That's where we concluded. So we will start. So we'll look at a few more convex functions today, right? So so the first result you have to remember is f Rn to R is convex implies, what can you say about the Hessian? What can you say about the Hessian? It's positive semi-definite, right? So, and if a function is positive semi-definite in its domain, then the function is convex. So it's an if and only if. Okay. So how do you verify a function is convex? Let's look at a few examples, maybe. Can you give me an example of a convex function? So let's look at the first example, which is norm. Why, for example, you have a norm in n-dimensional space, is it convex? Well, you look at lambda x plus 1 minus lambda y norm, which is less than or equal to norm of lambda x plus norm of 1 minus lambda y.